figuring out this whole thing is a grand adventure. Okay, Maria, Nick. Did I make Cade co-host instead of Evan co-host? That was a mistake. Sorry about that. Withdraw co-host position. So Evan, you should be able to get your presentation up now.
Yep.
I have, frankly, and Mick, and I'm getting there, guys. Frankly, Galini, Mick, Maria. How is everybody doing today? Still good from the very long time ago that I saw you, many of you, 2 seconds ago? I think Allison was going to do the introduction, so I just want to give her a minute or two. So if that's okay, we'll just wait another minute.
Go team. Hi. Oh wait, are you already started?
Nope, we were waiting for you.
Oh, good. Sorry, I had class and I just had to kick them all out. Okay.
Awesome. So I guess welcome to our 5th of the Senior Experience Talks in Chemistry. I really appreciate you all sticking with us in these Zoom sessions. We have today's talks, and we will be doing that in a second, but on Friday we have 2 more, again at 3:10 and then at 4 o'clock. So join us for those. And then next week we have 5 more, and then we have 4 more, and then we have 4 more. So we just have a grand extravaganza of talks, and I will continue to let you know when they are and and how to reach them, as they are a great opportunity to see our seniors shine. So I will pass it off to Allison Fleshman to introduce our speaker for today.
Go team. Well, first I want to say, yay, Maria. Forgive me, I missed your talk. I had class, but I hope it went really well. So yay to Maria again, because I'm sure it was fantastic. Okay, so it is my pleasure to introduce Evan Cline. He is from Freeland, Michigan. He came to Lawrence to defend our goals in the hockey rink, which I think is how you say that. But then he decided to join our chemistry team. I'm going to stop with yeah, okay, go team. Anyway, he's been working in the chemistry department. He worked in both Graham's lab as well as my lab. And I convinced him to do his senior experience project with me because every couple of years I wander down, or I guess I go upstairs into one of the synthesis labs, and I just kind of look for someone who will do synthesis for me because I don't want to. And luckily, Evan is quite skilled in synthesis, and so he agreed to work with me, and I'm excited for him to share, or for you to see what he's done, because along the way he taught me a bunch of synthesis, but he also learned a little bit about PChem. Actually a lot about PChem, and he's going to show some really cool trends that he's found, and he's also going to show basically that he's started on this project which became much bigger than we thought, and so it's only a small piece, but it's a really important piece in the grand story of my research. So I'm really excited to have Evan contribute to it. The other thing that's really cool about this is the stuff that he's learned specifically in the materials will serve him well, as he has been accepted and going to Dartmouth to pursue his PhD in material science and inorganic synthesis, kind of the combination of the two. So I'm really excited to see where he goes. The other interesting and awesome thing is that he appreciates IPAs and sour ales, which I highly recommend. He's got a good beer sense, which is just something that's fun to share. Okay, well, without further ado, I'm very proud and excited to hear what he has to say, and I'm happy he's going to share it with you. Go Team Evan. Yay.
Thank you very much for that introduction. Hello, my name is Evan Cline, and I will be presenting on the research I performed this year concerning the modeling of temperature-dependent conductivity within acetate ionic liquids using the compensated Arrhenius formalism. So I want to start my presentation with the question which is at the heart of this research's purpose. That question is, how do ions move in a liquid? Now, beyond just the realm of gravity, I wanted to understand how ions transport themselves in a liquid. In order to better understand what ion transport means within a liquid or any body of matter, it's important to understand what transport properties are. So transport properties are properties of all states of matter which are associated with the motion of mass, heat, electricity, and other properties as well. These properties rely on both the large-scale interactions of the materials as a whole and the small-scale interactions of the molecules. For example, viscosity, the measure of a liquid mass transport. Looking at this image, you can see how the liquid flows. The momentum of the liquid is due both to the entire substance as well as the nanoscale molecular interactions. Now, thermal conductivity and the electric conductivity are also transport properties, which are related to heat flow and electricity flow, respectively. So the rate of these flows is dependent on the materials which the heat or the electricity is flowing through. So here you can see the differences in the states of matter, solids having more cohesion than liquids, and liquids having more cohesion than gases. That's the material at large, but these conductivities, thermal and electric, are also dependent on those small balls which make up the materials, the molecules. So for reference, here's a water molecule with a sodium ion next to it for an example. So at the macroscopic level, conductivity is dependent on the state of matter, but the conductivity at the molecular level relies upon other factors, including the interactions between these molecules. So speaking of ions, another form of conductivity is ionic conductivity. This can be described as how ions are able to align themselves within a material, and it is more relevant to the question at hand. How do ions move in a liquid? So these three conductivities are similar, yet distinct and dependent on different factors. So conductivity, as I mentioned, it has several different flavors, but they all resemble each other in one way or another. So thermal conductivity has the units of watts per meter times Kelvin and can be thought of as heat energy per distance. Similarly, electric conductivity is the measure of electric charge per distance, and its SI units are Siemens per meter, which can be thought of as electric conduction per unit of distance. Lastly, ionic conductivity is a similar but different form of conductivity because it is a flux. Ionic conductivity is a measure of ion charges per area. So think of ionic conductivity as an ion moving through this cube-like lattice structure. It's important to think of these conductivities in two ways. First, it is key to understand the conductivity from a molecular level. But with that molecular understanding, I hope to expand it to a system level understanding of conductivity. As materials and systems become more controllable on the nanoscale, the demand for understanding how a system's intermolecular interactions contribute to their macroscopic properties increases. This leads me to the question of how we explain conductivity currently. So there have been two accepted models for ionic conductivity. The Nernst-Einstein Equation and the Vogel-Taman-Fulcher Equation. Chronologically, the Nernst-Einstein Equation came first. It relates molar conductivity, lambda, ion charge, the Z term, and temperature, as well as D plus and D minus, which represent the diffusion constants of the positive ion and the negative ion, respectively. The problems with the Nernst-Einstein Equation are nuanced, but I'll discuss the important ones. Because the Nernst-Einstein Equation is based on hydrodynamic theory, solutions which are not water-based do not work well within that system, or within the equation. Also, the equation has no inherent chemical approach to ions, instead treating ions as a point charge in a system, similar to a physics-based approach. So the Nernst-Einstein Equation cannot provide information about the local molecular environment of the ions. Also, and very importantly, this equation does not fit all experimental data, especially when the solvent is not water or if the solvent is less polar than water. So if it cannot fit data accurately and it cannot describe ionic conductivity at the local molecular level, the Nernst-Einstein Equation cannot help us learn how ions move in a liquid. So we'll go ahead and throw that one to the side. But the next model, the Vogel-Taman-Fulcher Equation, the VTF for short, it describes transport properties, expressly conductivity here, through an Arrhenius-styled equation. This allows the equation to accurately fit data because it addresses the observed exponential relationship between temperature and conductivity. If all we needed in this world was to explain data on a surface level, the VTF would be adequate, and I would spend my time fetching data to plot. But because it is both important to know how something is and why something is, the VTF falls short. The VTF equation can accurately describe a system's transport properties and fit data. However, it cannot explain transport properties at the molecular level. The VTF equation relies on empirical fitting parameters to explain the data. Instead of a theory or a model, the VTF purely draws a line from point A to point B. The result is that the VTF equation has two variables, the pre-exponential factor, the lambda naught, and the exponent B factor. Both are empirically fitted. Also, the TG and the T naught are system specific, thus they require extra data to obtain, which in general is inconvenient. To gain a more succinct and complete understanding of the data, we need a model whose basis is not merely translating the data, but instead taking a molecular approach to give that data meaning. A new model does exist, and it is the compensated Arrhenius formalism. This formalism bridges the gap which the VTF and the Nernst-Einstein equation create at the molecular level. The compensated Arrhenius formalism, the CAF, approaches transport properties from a molecular perspective, which allows the CAF to unify macro scale observations to nanoscale observations. Thus, we get the connection between nanoscale and macro scale properties, which provides a fit to experimental data, which is terrific. So the underlying molecular theory behind the CAF, which unifies those macro scale and nanoscale properties, is transition state theory. So commonly, transition state theory is utilized to explain chemical reactions. So here we have your reaction coordinate diagram with energy on the y-axis and reaction progress on the x-axis. The curved line leads from reactants to products, and it represents the energy level of the materials undergoing change. In order for those reactants to become products, they must reach an energy of activation. The energy of activation represents the highest energy of the reaction, and it is the barrier between reactants and products. Now, consider that instead of reactants, we instead have an initial state, and instead of products, we have a final state. This process is now not a reaction, but instead is a moment of transport for some observable property, say ionic conductivity. Now, the energy should be similar between the initial and the final state. So now the energy of activation represents an energy barrier between two states for that transport property. This activation energy can be due to a number of forces which occur at the molecular level. We can parse out a model from this transport-centric transition state theory. This diagram explains the theory behind the model, but as esteemed teenage heartthrob Juliet Capulet once said, "What's in a name?" Great question. So the compensated Arrhenius formalism. I provided the equation to look at as a reference. So let's start with compensated. The compensated refers to the model's compensation for not only the thermal dependence within the Boltzmann's factor, the EA divided by the gas constant times temperature, but also the thermal dependence within the exponential prefactor. Looking at the VTF equation in comparison to the CAF, we see that the exponential factor of that VTF, that being the Vogel-Tammant-Fulcher equation, has no thermal aspect incorporated, putting all the thermal information for the system within the exponent. The CAF addresses this by compensating for the temperature-dependent information within the system. The temperature related to the Boltzmann's factor, that being, again, the EA divided by the gas constant times temperature, and any other potential source of thermal dependency. So the Arrhenius refers to Svante Arrhenius. Everyone say hello to Svante, who developed the Arrhenius equation. The CAF resembles an Arrhenius equation, so Svante's namesake is incorporated in the name. Everyone say goodbye to Svante. The formalism aspect refers to the multiple equations which are combined to solve for the two unknowns in the CAF. That being the temperature-dependent exponential prefactor and the energy of activation required for the transport property. Thus, due to the multiple equations required to form the CAF, it is a formalism. So we have the compensated Arrhenius formalism, a model to describe transport properties. Now, let's use what we know about the CAF and go back to our initial research question. How do ions move in a liquid? So in choosing a system, we want to look at ionic conductivity. So ionic conductivity involves ions moving through a solvent. At the molecular level of many liquids, there are three types of interactions. You got solvent-ion interactions, sometimes referred to as solvent-solute. You've got solvent-solvent interactions, which is basically the solvent bumping into itself, and ion-ion interactions. With a focus of learning more about how ions move, we wanted to focus on maximizing ion-ion interactions while minimizing the other two. In fact, let's just use a system of only ions. Room temperature ionic liquids, which have already successfully been applied to the CAF, consist solely of ions in the liquid form. Room temperature ionic liquids are a unique type of liquid, and as previously with the CAF, I will break down the name. So I've mentioned the room temperature ionic liquids, but I have not gone into depth about why we use these solvents as a model to test the CAF. So a room temperature ionic liquid. In pieces, starting with the ionic aspect, what is it? So ionically, think of salt. I've provided the picture of salt, which many of you are likely familiar with, but truly any salt would do for this part of the story. Salt consists of two ions, one positive ion, the cation, and one negative ion, the anion. They are held together by an ionic interaction where the positive charge is attracted to the negative charge. So table salt's two ions are sodium and chloride, which is what this image is representing here. The green balls being the sodium and the purple balls representing chloride. Here they form a solid. Now I want to tackle the liquid aspect. So going back to early scientific instruction, You learned about the forms of matter: gas, liquid, solid, and of course, you can't forget plasma. So more about liquids, they're a curious form of matter. They can take the form of any container which they are in, whether that container is a plastic jug or a large depression in the earth between Michigan and Wisconsin. Either way, the body of a liquid forms to the container while also holding on to the surrounding molecules. So we have a liquid which is molecularly made up of a lattice of ions, a lattice being this image right here. And that lattice is free-flowing. However, the ionic interaction is constant. The room temperature part, it refers to the material's capacity to maintain liquid form and ionic interaction at ambient temperatures. So that's the gist of room temperature ionic liquids, also known as RTILs for short. The physical properties which room temperature ionic liquids possess are remarkable. They boast low vapor pressures, so they will not boil or evaporate, barring extreme measures. Also, room temperature ionic liquids have high thermal and electrochemical stability. This means that room temperature ionic liquids require extreme temperatures or extreme electric currents to affect its chemical bonds. Sorry about that. I've described the room temperature ionic liquid as a concept, but I want to clarify what these molecules look like. So this is what a room temperature ionic liquid looks like in the flesh. It's a thick and slow-moving liquid, and that's due to its molecular properties. So on the right, we see what the liquid looks like at a macroscopic level. However, on the left, we have a geometric drawing which represents the molecule. The difference is the one on the left is microscopic, that being the one on the left is molecular. It's a molecule in its atomic form. So I would like to point out the parts which I have previously described to you. So first off, I'll start off with the name and the shorthand. This molecule is called 1-methyl-3-octyl-imidazolium trifluoroacetate, and the shorthand for the molecule is C8-MIM-TFA. The C8 refers to the alkyl chain right here, and the 8 points coming off of the N, the nitrogen, refer to the 8 carbons, hence C8. This part is the anion. This specific anion is trifluoroacetate, or TFA, as you can see in the shorthand. And here's TFA in its full drawing. So this aspect of the RTIL provides the molecule with many of its electronegative properties, as it holds a negative charge. Lastly, this part is the cation. The imidazolium piece, abbreviated MIM in the shorthand, provides the liquids with the positive ionic charge. The imidazolium differs in its alkyl chain length for each molecule in this study. In this study, I used the same cations, imidazolium with varying alkyl chains, but I used 2 different anions, trifluoroacetate and acetate. For example, here's that cation with an acetate anion instead, and here's what the acetate anion looks like. So when comparing acetate and trifluoroacetate, these 2 anions help to narrow our question and look at how ions move in a liquid to how these specific ions move in a liquid. They both have a high capacity for gas adsorption as well, which will come in handy later. They are the 2 anions used in this study of the compensated Arrhenius formalism. So with the cation, the anion, the alkyl chain, and the molecule shorthand fully explained, I present to you the full family of liquids used in this study. And here they are, a full portrait of the molecules used in this study. On the left side, we have a family of imidazolium trifluoroacetate, or CN-MIM-TFA, ionic liquids with varying carbon chain length. And on the right, we have a family of imidazolium acetate, or CN-MIM-AC, ionic liquids, also with varying carbon chain lengths. With the help of Dr. Fleshman, I decided that these families would be the best for our testing based on the chemi-adsorption properties which these anions have. So these 2 families differ in their anion. However, their anions are similar in molecular structure. Thus, if we measure a difference in between the 2 groups of ionic liquids, the difference will be almost solely due to the anionic properties. This may allow for further understanding of the results when other anions are interchanged with imidazolium cations. So essentially think of this slide as like a Pinterest dream board. I wanted these molecules. So first I visualized having them, as one must do. But the eventual goal was to make this dream a reality. So luckily, the action was taken. Again, thank you, the Chandler Senior Experience Fund. Sorry, it always gets me. So as is common in life, everything can be bought for the right price. So using this fund, once again, thank you, we bought a majority of the room temperature ionic liquids. However, if you may have noticed, there are two missing, those being the 1-methyl-3-hexylimidazolium trifluoroacetate, C6-MIM-TFA, and 1-methyl-3-octyl-imidazolium trifluoroacetate, C8-MIM-TFA. Those two ionic liquids were not in the budget. Luckily, their starting materials were. So with the time on my hands and the proper conditions, reagents, and training, I got to work on synthesizing the remaining two RTILs. So now I kind of want to take a broad, take a step back idea of how synthesis works. So I describe it as similar to baking. So first you have an end goal in mind. For example, this chocolate cake, or maybe a different type of dessert, or maybe something completely different because you've spent this entire quarantine baking. Regardless, you have a product in mind. Next, you formulate a procedure or a recipe to combine or synthesize the ingredients. You could call this a synthetic strategy. Personally, I'll call it a synthetic strategy. So next, the ingredients for the cake represent the reagents within this analogy. So once you have those reagents, a synthetic strategy, and an intended product, you can apply the proper conditions represented by this arrow. For a cake, this might include an oven at a specific temperature, maybe a baking pan, or maybe even mixing the ingredients together. So the specific conditions are outlined within the recipe or the synthetic strategy. So finally, once that process is over or the reaction is completed, you isolate the intended product. So for the cake analogy, perhaps you move it from a baking sheet to a nice plate and you put icing on it. This part of the isolation process can be thought of as the workup, and you've done it. Nicely done. So now I'll get into the synthetic strategy which I employed. So using a known synthetic route, we can make the precursor to one of our eventual molecules. So starting with the reagents N-methylimidazole and 1-bromohexane, I combined them in a sealed flask, and the sealed flask also contained isopropanol as a solvent. The reaction mixture was heated to 80 degrees Celsius and stirred for 3 days. The product formed was 1-methyl-3-hexylimidazolium bromide. With this product form, we could move forward to the next step of the synthetic strategy. However, before I describe the next step, I want to show you the mechanism for this reaction. So essentially, I've shown you the drawings of what is made, but I want to tell you how this eventually became this. So the mechanism for this step resembles an SN2 reaction, better understood as a second-order nucleophilic substitution. So starting with N-methylimidazole, observe the lone pair on that nitrogen. This lone pair represents 2 electrons, and the nitrogen represents our nucleophile within this reaction. The other reactant, 1-bromohexane, is our electrophile, meaning that it is attacked by the nucleophile. So the nitrogen's lone pair attacks the carbon which is bonded to the bromine, which in turn breaks the bond between the carbon and the bromine. The resulting product is 1-methyl-3-hexylimidazolium. There is a positive charge on the nitrogen now, as it has 4 bonds, which is one above nitrogen's standard valency. And lastly, the bromide ion's negative charge is attracted to the positive charge of the nitrogen, and the resulting ionic attraction forms this precursor, 1-methyl-3-hexylimidazolium bromide. So, moving forward with that, the 1-methyl-3-hexylimidazolium bromide from the previous step was then combined with trifluoroacetic acid in an airtight vessel. Acetone was used as the solvent, and the reaction vessel was stirred for 3 days at room temperature in an air-free setting. After 3 days, that product was isolated, and that product being 1-methyl-3-hexylimidazolium trifluoroacetate. So with this product formed, it needed to be purified. So purification is an important step in synthesizing a quality product with minimal byproducts or impurities. The purification, including rinsing the final reaction mixture with solvent and attempting to separate the product from unreacted excess reagent, which I've shown here in the picture. So this will eliminate much of the excess unreacted reagents which are still in the solution. However, to ensure that only the pure product remains, it is important to rely on what you know about the product. With room temperature ionic liquids, we know that they have negligible vapor pressure and high thermal stability. So in synthetic terms, it does not boil or evaporate, and it's difficult to burn. Thus, you can remove almost any impurities by heating it and pulling on the solution with vacuum simultaneously. So that is what I did. After every step, which I will show you, once a product was formed, that product was separated from excess reagents and heated above the temperature which the solvent should boil at, while simultaneously a vacuum lowered the pressure of the system for 3 days. One might say that it was overkill to purify for so long, but as a wise synthetic chemist once said, if you put junk in, you get junk out. So any purification done early within the synthetic route should lead to time saved at the end of the synthesis. So with the C6 MIM TFA formed, the C8 MIM TFA synthesis remained. So this synthesis is identical to the prior synthesis, fortunately. So the N-methylimidazole and the 1-bromo-octane are added to a reaction vessel with isopropanol acting as a solvent. And then the reaction mixture is stirred at 80 degrees Celsius for 3 days, upon which 1-methyl-3-octylimidazolium bromide is formed. And then this product was purified and moved on to the next step. Once you have that 1-methyl-3-octylimidazolium bromide and trifluoroacetate joined together in an airtight vessel, you can add acetone as the solvent, and the reaction mixture stirred at room temperature for 3 days results in the product 1-methyl-3-octylimidazolium trifluoroacetate, also known as C8-MIM-TFA. The product was purified and stored. With the synthesis complete, the product was stored for later use. So here are the final products in their glorious liquid forms. The 1-octyl-3-methylimidazolium trifluoroacetate and 1-hexyl-3-methylimidazolium trifluoroacetate from left to right, respectively. So it's important to celebrate the little things, such as a successful synthesis. However, it's even more important to put these materials to work. But before these two thick fluids can be cleared for work, their purity must be determined. During the synthetic process, I took time to ensure the purity at each step. So I assume pure products were formed. However, assumptions do not always result in good data. So to ensure the purity of these products, I tested for the primary impurity that had the greatest potential to contaminate my solutions. That molecule, which makes many air freak chemists quake, the mischievous water molecule. I provided mischievous apparel to demonstrate how sinister this molecule could be. I, with the help of Ricky Pena, tested these two samples for water content by utilizing Carl Fisher titration. So I know that I just portrayed water in a very negative light, which is unfair. To most of the world, water is a very valuable resource. However, to certain synthetic chemists, water is detrimental to the quality of a product. In my instance, water can disrupt the ions within a room temperature ionic liquid and alter the transport properties. Now, ideally, I don't want any water within my samples. However, time is also a valuable resource, and a lot of time may be required to ensure that all of the water is removed from a room temperature ionic liquid. Thus, if there was water within the samples, minimal water is a trade-off for a shorter purification period process. So the industry standard water content test for room temperature ionic liquids is Carl Fisher titration. And here's the apparatus. So the process works by placing fractions of the sample within the testing cell here. Then KF reagent is pumped into the cell to react strictly with the water within the sample. These here are the reactions which take place within the cell. B represents a base, which in this instance is pyridine, for anyone who is wondering. The KF reagent is used as a titrant to detect the amount of water within the analyte sample. The iodine has a stoichiometric 1-to-1 ratio with the water within the ionic liquid. The apparatus will end the titration when all the iodine has reached the water, has reacted with the water, which is detected by the anode within the cell. When the iodine has fully reacted with the water, the platinum anode will detect excess iodine, and the apparatus calculates the water content within the volume of the fraction. My samples contained anywhere from 3% to 0.5% water by volume, which is a moderately high in comparison to industry standards. The next step was ionic conductivity. So thermally dependent conductivity data is required for ionic conductivity within the CAF. To get this data, I took samples of each ionic liquid from both groups, the two groups being the acetate anions and the trifluoroacetate anions, which added up to 8 total samples. So prior to testing the samples, a potassium chloride sample was used to standardize the cells within the apparatus. The standardization determined the distance between the 2 prongs on each of the probes being used to test for the conductivity. So between these prongs is where the actual conductivity is measured. With the standard determining the cell's potentials, the ionic liquid samples were ready for conductivity testing. Placing about 0.8 milliliters of sample within each cell being represented by this jar, the apparatus took multiple conductivity measurements at 5-degree increments as the samples heated from 15 degrees Celsius up to 90 degrees Celsius. And then back down in 5-degree increments again from 90 to 15. The resulting data is plugged into the CAF, and we were able to see if the CAF could model the ionic transport or the conductivity of the ionic liquids. So here are the results of the conductivity in relation to temperature. This graph represents the relation between temperature in Kelvin and conductivity in millisiemens. For 1-methyl-3-octyl-imidazolium trifluoroacetate, from initial observations, it's encouraging to see the exponential relationship between the temperature and the conductivity. And unfortunately, I was not able to get experimental density data before losing access to the laboratory. This density data is crucial for the CAF, and it is incorporated into the pre-exponential factor. However, as you can see, this data is for C8 mem TFA. However, a comparison between the C8 mem TFA and C8 mem AC shows that the anion does in fact impact the conductivity of the ionic liquid. While this is not a finite answer to the question, how do ions move in a liquid, these results demonstrate the effect which an anion can have on a room temperature ionic liquid. So for future plans, the next step is to take experimental density data. This will make the conductivity data applicable to the CAF. Thus, it is crucial moving forward to take this density data. Also, the purity of the homemade ionic liquids is somewhat questionable. These materials are very difficult to purify due to their inert nature, and we want to make sure that if we're plugging these materials into the CAF, that they are as pure as possible. Also, once that is done, we want to test the gas absorption capacity of these ionic liquids. So I mentioned earlier that these 2 anions, trifluoroacetate and acetate, are both highly chemiabsorptive. So the next steps in this experiment include seeing both how well these liquids can absorb the gas, but then also retesting the conductivity of these gas-laden ionic liquids. So I want to give my thank yous. So first and foremost, I'd like to thank the Chandler Senior Experience Fund for funding my research project this year. I would also like to thank my chemistry instructors, Deanna Donahue, Stefan Debert, Graham Sazma, and Allison Fleshman, who have helped me develop into the student and chemist I am now. I would also like to thank my lab mates and my classmates over these 4 years, with a special thank you to Ricky Pena for helping me perform the Carl Fisher titration measurements. I would also like to give a tremendous thank you to Daniel Martin, who made ordering reagents and apparatus seamless over my 4 years at Lawrence. You helped orchestrate experiments at Lawrence, and I thank you for the work you do. And I also thank the stockroom employees as well. Lastly, I want to give a special thank you to Dr. Allison Fleshman for taking me on to work on this project. You allowed me to approach this task from a synthetic bent, and you guided me through the physics of this research. I can firmly say that I am a better chemist now. Here are my sources, and I'm open for questions.
Hey, sorry, took me a while to get unmuted. Thank you so much. Any questions?
I was wondering, how would the water impurities in the ionic liquids affect their conductivity measurements? Like, do you have any idea which way it would skew your measurements to be trying to compare your personal synthesized ones that are maybe lower in purity than the ones from the other department or other place?
So like how it would impact the conductivity?
Yeah.
I would believe that it might actually increase the conductivity because water has a high dielectric constant in comparison to these room temperature ionic liquids. So whereas the ionic liquids might like pass the ionic charge along to each other at a reasonably constant rate, temperature dependent, of course. With water in there, I'm pretty sure it develops these kind of like pockets of water where the charge, the ionic charge can move a little bit more quickly. So if there's more water within the sample, it could be theorized that it would be likely to be more conductive.
Stefan Debert has a question.
To ask a couple questions off of Evan. So one, at what point do you said you had up to 3% water. So at what point do you start to get worried that that's having too much of an effect? And then two, at what point do you consider taking steps to dry it? And then how would you go about drying these things?
So 3% is definitely a concern. So I kind of glazed over the purity because I really would have liked to take more KFT measurements because they were pretty variant. We observed like every time we take the first sample, it would give us a reading of about like 3%. However, the next 5 or so samples would give us a reading of about 0.5. So I wasn't able to, perform more experiments to determine how much of it was, drift versus how much of it was error. So I can't give like a certain answer as to the purity. But as far as taking more time to dry it, I did mention that each step, like the purification, I put it in a wax bath, 90 degrees, stirred it for 3 days on the stronger than house vacuum. So I'm unsure. I would assume that to get more water out, thinking of water as the only contaminant right now, to get more water out, I would probably just put it in sieves. But then just like physically, it'd probably be really frustrating because the sieves within that extremely viscous liquid would be pretty hard to distribute. However, fun little side story, I tried to get the water out by putting it in the vac oven, and I pulled vac too tightly and didn't have my vessels sealed well enough, and the first batch of ionic liquids sprayed everywhere within the vacuum oven. So I guess this one here is to undergraduate research and making mistakes when they
Good
don't
times.
count.
Yep, cool.
Other questions?
I just wanted to chime in with a comment. So to the question about what happens with when you add water to the conductivity, yes is the answer. It goes up and it goes down. It completely depends on which ionic liquids you have because the variability is so vast. So there have been both. So what Evan said is true. In certain cases, you will see an increase in the conductivity because of the dielectric properties of water. But then in other cases, you'd see a decrease, which just makes these things very, very different all across the board. So all the more reason to get no water. No water. Come on, synthesis people. Improve your techniques. I say with love.
Is that a question, Graham?
It is. Evan, can you comment on the color of your ionic liquids?
Nice. Yeah. What's that?
Colorful.
Sadly, they're just kind of, well, not sadly. No such thing as sad color. It's like a deep amber hue. Let me get back there. Kind of reminds me of like amber, which you notice in like fossilization. It's like a really deep, really dark brown. And I don't really have any information as to like what the color entails. because there's not that much, I guess, information regarding like what gives ionic liquids their colors right now. I can tell you that the colors of these ionic liquids were different from the like the purchased ionic liquids. However, the purchased ionic liquids also had variant colors. So it could be thought that maybe it's due to impurities within the ionic liquids, but it's really kind of up in the air, and I can't give a solid answer to that.
That's a good pun.
Thank you.
Other questions?
Could it be that some of that color could come from oxidized amine impurities, right? So if these things are made, I assume by some kind of amine substitution reaction. So if you had any amine left over, that could get oxidized and would turn pretty brown for you.
True. I was also wondering if it had to do with bromine reacting with anything else, just because bromine is known to have that kind of deep red, amberish color at times. But again, I didn't run any further purity other than testing water content. I think the next like test that would be performed was to titrate it with like silver nitrite, because that would be able to precipitate out the bromine. But again,
yeah, we can draw a distinction between bromide and bromine here, right? So unless you're like strongly oxidizing it, it's any Br would be a bromide, so it wouldn't be colored. But yeah, definitely.
Can you purify the ionic liquid by column or ion exchange resins or something like that?
Potentially. I know that like as far as time wise, these ionic liquids are a very slow moving body. So I didn't really want to have to use a column for them. So I tried to just kind of do it rapidly with a, pulling vacuum while also applying heat.
Is that because any solvent is bad?
Yep.
But would a lower boiling, less sticky solvent than water potentially be a better solvent for you?
Oh, definitely. I didn't, there was no water used as a solvent. It's just water that was kind of, because I didn't dry, the only reagents I dried were TFA and acetone. So I didn't dry my, when I say dry, I mean like put on molecular sieves. I didn't dry the bromohexane or the bromooctane, and I didn't dry the N-methylimidazole. So that would also definitely help with the purity, because again, junk in, junk out.
Other questions?
I have a question. So did you see any like glaring like trends between the synthesized products and the ones that you bought when it came to the thermal conductivity measurements? Like, were there differences, unexpected differences between the two?
Yes, but also no. So it's tough because it's expected to see, like, you're going to see extremely different conductivity between like C2 versus a C6, because when you have so few carbons, the dielectric constant is going to be completely different. And then you can't really compare the C6 trifluoroacetate and the C6 acetate, because those fluorines are going to also have such a huge impact. Truthfully, it would have been nice to take extra data and see that, extra measurements and see if there was a difference there. But I would assume there would be some sort of difference dependent on how many impurities there were. And looking for other impurities, like other than just water, would have definitely shed more light on that, but I'm not sure.
How might you look for other impurities?
I would probably do more literature research to look into how other groups have purified their ionic liquids and see what they have tested for, especially focusing on acetate anions, because they can be really tricky. So I mentioned their ability to chemi-adsorb, so they can take gases in really well, which is great when they're taking in the gases you want to take in. But when you've got all these other impurities within a lab that you can't really account for, maybe they were adding those as well. But again, more time would have been nice.
It seems like we're going to wrap up the questions, so I would like to thank Evan again. Thank you so much for the talk. Great job. I would like to also invite everybody to the talks coming up next Friday. Galini will be going at 3:10, and then Katie will be going at 4 o'clock. So we have 2 lovely talks on Friday, and you are welcome to join us. Feel free to stay behind and ask Evan any questions that you would like to ask, but otherwise, thank you for your time, and I will see you when I see you next. Great job, Evan.
Thank you. Thank you.
Sorry for jumping. I had a meeting I had to run in and jump out, so I caught the back half of yours and the front half of Maria's. So look great.
So Stefan and Graham, go team. This project is going to continue on, so be thinking about purification, because just saying, I don't want to do it.
Boil the crap out of it, right? Because anything the thing that you want won't boil, and the stuff that you're worried about will. So just build a goddamn cauldron and just kind of.
Methylamidazole boils at 198.
Yeah, man. Which is to say a number.
Let it rip.
Yeah, they just at Oak Ridge they just like left it on sieves and in the vacuum oven for like months and months.
I think that the key, and Evan alluded to this, the key is making sure your starting materials are pure before you go in. So really, I think it's that methylamidazole to start with. You really got to purify that, and that's a, like as Graham said, that's a high listed boiling point, but chemists distill stuff like that every day, so that's doable.
I was looking into purifying the N-methylamidazole using that nice big book of purifying organic compounds, and I saw the temperature and I was like, you know what, maybe I'll just try to take stuff out later. But I mean, that probably is what ended up. Yeah,
I mean, and you've heard us talk dreamily about a Kugelrohr instrument. Like that's where your Kugelrohr pays for itself, is trying to distill away very high boiling stuff. So that's how you purify that. You'd have to go there.
Exactly.
But go ahead. Sorry.
Did you try the IPA when you used it? Not the beer, the solvent, isopropyl alcohol.
I didn't try that. No, I was very excited to use it though. I haven't used isopropyl alcohol as a solvent before.
Well, as Allison said, we have some kind of model for how we would expect water to confound some of this data. I don't have any idea about how I would expect amines and amine oxides and random stuff to confound this data.
Well, and the back to the color question, that's a hot debate on how much does the color affect impurity, or is it from impurities? Some people think, especially with the longer chains, if you set these things up to where you've got the longer alkyl chain, some people think that there's actually a coordination between the alkyl tails, and that's creating some sort of chromophore across the imidazole ring that you can have. This is when I was doing the fluorescence work at Oak Ridge. They think a lot of the fluorescence is coming from these coordinations, or this kind of almost dimerization of the nonpolar parts. And so they think that there could be some colorant coming from that, because a lot of pure ones are just a hint yellow, not that black though.
I think that on the one hand, I totally agree, and I've seen it. I've made aromatic carboxylic acids that are purple, and I couldn't figure out what the hell was going on, and I think that's definitely the case. On the other hand, though, I think when you see brown, right, it's kind of one of those when you hear hoofs, don't think zebras type of situations.
Go team.
I like to think about zebras, though.
I mean, they are kind of cool. But anything that fits nicely into my organic chemistry rainbow of white to yellow to brown to black, I think that's my first guess.
But yeah, the store-bought ones, essentially, they're a yellowish, aren't they, Evan? They're kind of pale yellow.
They're either clear, they have a yellow tint to them.
Yeah. So that's the color that they're thinking is causing. It's from that dimerization, possibly.
if you trust that manufacturer to have, for instance, purified their amine and such.
Sadly, they are Iolatech, Ionic Liquids Direct to You.com. No, I mean he's legit. But and it's one of the reasons that they're so expensive. These two especially were the most expensive because I think the purification just takes for freaking ever.
Yeah.
Yeah, I think buying these, the rest of them were about maybe 200 a piece. I think these were about 800 a piece for 5 grams.
So go team.
Yeah, we could. This will be the 485 project next fall, right? That'd be perfect because we would work in.
Look at Allison's excitement. Blew her
Yes.
mind.
I'm not kidding. I mean, when I think about what are the skills that we should really be teaching in that class? Yeah, vacuum distillation, high temperatures,
It's hard.
stuff air free. Let's do that.
And the synthesis is easy, supposedly. Y'all keep telling me it's an easy synthesis, and it looks like
easy synthesis.
I can follow the arrow pushing.
Yep.
But no, that would be yay. Yep, let's do that.
Yeah.
If we're in class.
So I still want to hear, Allison has suggested a new acronym for the CAF of MTSTT, right? And I want to know how you would say that acronym.
I hate the name. So my postdoc colleague, the Compensated Arrhenius Formalism, I hate it. It's a modified transition state theory of transport. MTSTT. It's
Sorry, I'm just saying that's hard to. It's hard to say.
It's anyway. It's better than hydrodynamic theory.
Whatever Fleischmann curve, call it.
The Fleischmann curve. Actually, we make the curve straight. That's the kicker.
Well, that fix it. Fleischmann line sounds different. So I don't know what you're. That's like the batting average that gets you sent down, right? It's like the Mendoza line, but
yeah. All right.
Cool.
Well,
looks good.
Team.
Good work.
Nice job, Evan.
Thank you. Thank all of you. I appreciate the help that you've given me throughout these 4 years very much.
Yay.
Absolutely.
I'm going to cheat and say, Allison, I read the questions for tomorrow.
Oh, perfect.
Yeah, it's fine.
Are we good? Are we happy? Evan, we're talking about something else. Sorry.
Oh, you're fine.
Are you
Good.
good?
Your part moving so fast I didn't even notice. Yeah. Yep.
Okay.
Cool.
I had
Have a
an
good
email,
day,
but-
Evan. Thank you so much. Good job. Have a beer. Oh, he left before I said have a beer.
Go team. Yeah.
We're still recording, but yeah.
Oh, I'll stop. I'm so sorry. Thank you for reminding me.